Welcome to another video in our physics class. In today's video, we're going to be discussing graphing uniform motion. For those of you who are following along in the packet, this is on page 23, and the rest of the information will be on page 24. In the last video, we discussed drawing proper best fit lines, as well as how to calculate slope properly using the correct equation. Now we're going to go ahead and put those skills into use on these pages. Now, in a normal year, you guys would be taking these data yourself. However, this is not a normal year, and I am providing these values to you. So feel free to go ahead and pause this video and write down these values. And we will be using these to draw our points and our lines. Just as a reminder, the best fit line, we have to try to touch as many points as possible. Do not draw the line from 0, 0. Do not use existing data points to find your slope. And the coordinates and the points that you use in order to find your slope should be far from each other for the greatest accuracy. So these are just some tips in order to have the best fit lines available. I'm going to go ahead and give you a few minutes to draw the graph, and you will see what your graph will look like compared to mine. So go ahead and pause this video, and we will resume in a few seconds. All right, now that you've had time to draw your graph, hopefully it looks something similar to mine. I doubt that it will look exactly like mine because the increments and so on. But I'm going to go ahead and explain why I did it and how I did it. Now, if we looked at the table, our range of values for the x-axis for the seconds was from 0 to 3.44. It's always a good practice to go above your typical range. And in this case, in 3.44, I went ahead and decided to go all the way up to 4. The next thing that you should do is count how many lines you have on the x-axis. When you count the lines on the x-axis, we notice that we have 10 lines, and we could dedicate about 0.4 to each one. This is useful because it allows us to space out the line and our data points as much as possible in order to get the best reading for it. On the y-axis, it was already done for us, so we really couldn't do much. But we had free range in our x-axis. Now, you see my black dots. Those are my actual points from the data set. I am not using any of those to find my slope. Instead, I am using the open circles that are going to be used for my coordinates for my slope. The first one on the left would be considered my x1 and y1 values, and the second one is going to be considered my x2 and y2 values. As you notice, I have dotted lines going all the way down to the bottom on the x-axis as well as on the y-axis. I recommend doing this because it helps you be able to read a graph properly and identify your points. If you try to eyeball it, there will be times where you will mess up. So avoid mistakes as much as you can. Now the full page of mine looks something like this. I have placed everything that I can. Again, we have the equation for finding slope on the right, which is m is equal to y2 minus y1 over x2 minus x1. Again, pay attention to the warning. Please do not use the method that your algebra teachers love to teach you. That method will not work in physics classes. As I've said before, if you attempt to count boxes, or if you're tempted to count those boxes for whatever reason, just save yourself the time and the hassle, because the end result is going to be the same thing as you never attempting it. You're going to get 0 points. You will be wrong every single time. Moving on to page 24, there are some questions that you will see. Those questions will be answered by you. And the piece of information that you see down here, you can go ahead and add it at the bottom of page 24 or write it somewhere in your notebook. This information is crucial in order for you to read and understand what is happening in a motion graph. Both of these graphs are a position, or essentially a distance versus time graphs. Time will always be on the x-axis for us, and the y-axis will either be the position, the distance, or the displacement, and so on. But time will always be on the x-axis. Looking at the picture, or looking at the graph on the left-hand side, the very first line in blue that we see would be considered to have a very steep slope. Anytime you have a steep slope, that means that you've got a very fast velocity, because in a very short amount of time, you've traveled a great amount of distance. Go ahead and think of it as essentially a slide. If you place the ball at the very top of that slide, the ball will go ahead and roll down at a very fast rate. Now, as we go to the right and we see our first red line, at that point, the object is considered to be stopped, and the velocity there is 0. We know it's stopped because the position is not changing, but time is moving. Going to the line to the right of it, we have what's considered to be a gradual slope. In this case, we have a slower velocity compared to the steeper slope that we saw in the very first line. It takes us a lot longer to travel that amount of distance compared to the rate that we were doing originally. In the fourth line, again, the object is stopped. Velocity is equal to 0 meters per second because the position is not moving, but time continues to go. And finally, the fifth line, we have what's considered to be a negative slope. And in this situation, it is also a very steep slope, which means that not only is it going very fast, but it's going backwards. And it ends up being back at the starting position. Let's go ahead and put an example or real-life scenario behind this motion graph. Let's say that you're running late for something and you rush out of the house and you speed your way all the way to a red light. So while you were speeding, that would have been the very first line that you see, going a very high amount of distance at a very short amount of time. Eventually you hit a red light, you can't go anywhere, and you're stopped, but time is continuously taken away. While you're stopped, you notice that a police officer pulls up next to you, and when the light turns green, you can no longer go at the speed that you were going previously. Instead, you have to go the speed limit. So the third line, we notice that you're going slower compared to what you were doing originally. Again, you hit the red light, and you have no choice but to stop there. While you're at the red light, you notice that you may have forgotten your phone, and therefore you rush back as soon as you can at a very fast rate, going back to home, which is your fifth line. So that's an example of a real-life scenario or a story that would explain what the graph is doing there. Now, on the right-hand side, we have the different types of slopes that we would see. The very first line on the left, that's got a very steep slope, that's going to have the fastest velocity. That's faster relative to what's considered to be the original slope in the red in the middle. And compared to the red in the middle, the one below it would be considered a gradual slope or less steep. And that would mean that you've got the slowest velocity. So if you're ever in doubt in a position versus time graph or a distance versus time graph, think of the line as a slope, think of the line as a slide and pretend there's a ball there. Imagine how fast or how slow it would take for the ball to roll down. That would give you an idea as of, are you going fast, or are you going slow, or are you just going at a normal pace? Okay, with this piece of information, you should now be able to answer the rest of the questions, starting with number 4 on page 23, and the rest of the questions that you would see on page 24. That concludes today's lesson. Have a wonderful day.